routing between VLANs. So we've seen how we can make our broadcast domain smaller by putting our devices into separate VLANs. Now we're going to have a look at how devices in different VLANs are able to communicate and share resources with each other. So why do we need routing between VLANs? It's very simple, really. With VLANs, we're able to put our devices into different broadcast domains. So because they're in different broadcast domains, they're in different subnets, in different networks. But even though we want to have separation at layer 2, we still want devices in our enterprise network, in our business, we still want those devices to be able to communicate. So there's no point in having VLANs if devices can't communicate, because that essentially breaks the whole idea of a network. In a network, we still want devices to be able to communicate, but we still want to have the benefits of VLANs, where we have smaller broadcast domains and we have some security at layer 2. So we need to use a layer 3 device in order for devices in different VLANs to be able to communicate. This can be a router or a multi-layer switch. So method 1. So the first method that we can use to allow devices in different VLANs the ability to communicate and share information would be to use a physical router. So a router and a switch and separate interfaces connecting to that router in different VLANs. So as an example, if I also draw a sample basic network very quickly. In this case, we have this device, PCA, which is in VLAN 10, PCB, which is in VLAN 20, with a connection to a router. So it connects to a switch, which connects to a router. This switch, for method 1, would have a separate connection for each VLAN that is configured on that switch. So in this case, we've got 2 VLANs, so there would be 2 connections to that router, and each so on the switch, each link would be in a separate VLAN, and each connection would connect to a separate port on the router. This is the easiest method to configure, and the router operates as normal, as it just routes traffic between VLANs like normal. It's saying that it's routing traffic between different networks / subnets. The problem with this is we need a different link for each VLAN, which means that if we had 10 VLANs, we would be consuming 10 ports on both the router and switch, because we would need 10 different links for each VLAN. And so it's not a very, very scalable method to use, because the more VLANs we have, the more connections we would need to have to the router. So if we had 10 VLANs, we'd have to have 10 connections. If we had 100 VLANs configured on the switch, we would need 100 individual links running to the router, which doesn't make this very scalable. And on each interface, the router would have an IP address for the different VLANs. So in this case, if we use a network for VLAN 10, 10.1.1.0.24, that means that the router would have to have an IP address in that network. And so this kind of shows a physical representation of the first method. So we have the switch here. We have 2 devices which connect to the switch in different VLANs, and we would have to have a number of connections to the router, and that is dependent on the number of VLANs we have configured. So in this case, we have 2 VLANs. We want this to be able to communicate. So we have 2 connections to the router. Each is in a separate VLAN. If we had 10 VLANs, we would have to have 10 connections each in a separate VLAN. Like I said before, these would connect to different ports on both the router and switch, which would consume available ports, and we'd have to configure an IP address on each port in the subnet that assigned to that VLAN. Now, the second method, known as router on a stick, uses a single connection between the switch and the router to carry traffic for all VLANs over that single connection. So what we actually do, we configure a trunk link running from the switch to the router, and that trunk link carries traffic for all of our VLANs. Now, we would configure what's known as sub-interfaces on a router to support multiple VLANs over a single link. All sub-interfaces are logical interfaces. So draw a router very quickly and a switch. Imagine this is our link. With sub-interfaces, all we're doing, we're splitting up this physical link into multiple logical links so that the router can support receiving traffic by different VLANs over a single physical connection. We would then assign each sub-interface to a different VLAN. So in this case, just to make a very basic example, we have a trunk connection here to a switch. Let's say we have VLAN 10 and VLAN 20. So we would assign one sub-interface to VLAN 10 and one sub-interface to VLAN 20. So that now when the router receives traffic from VLAN 10, it doesn't see that traffic as coming over this physical link. It sees that traffic as coming in via this sub-interface, via this logical connection, and leaving this logical interface, which means that in logically the router sees the traffic as entering and leaving two separate interfaces, but in reality that traffic is being carried over one link. The router just thinks it's leaving two separate physical interfaces. In reality, it's still going over a single link. This is scalable because we can use one trunk link to support multiple VLANs. The problem is it can cause a bottleneck. So if we're using a single link to carry traffic between our different VLANs, that means that if we have a lot of traffic moving between our VLANs, that traffic can be bottlenecked here, which will slow our network down. Because we're using a single link, the router is limited to how fast he can receive and send traffic back at that same link. And the physical interface is still used to transmit our data. So this image shows a logical representation of the router on a stick method. As you can see, we can use a single physical interface to carry traffic for multiple VLANs. We have the VLAN 10 and VLAN 20. And as you can see, the router sees these sub-interfaces as separate interfaces, which means that traffic from VLAN 10 will come in via this interface, which the router sees separate to this interface. So in the router's mind, it's forwarding traffic out a different interface, but in reality, the traffic is passing back over the same link. Method 3 is known as inter-VLAN routing. So with the third method, we would actually use a layer 3 switch to route traffic between our VLANs. Now the benefit of this is that traffic can be routed between VLANs much faster because it's all performed at wire speed by the switch itself. And so what we would do, we would configure what's known as switch virtual interfaces on the switch for each VLAN to allow routing of traffic between those VLANs. And it's like the switch having an inbuilt router. So you can imagine this is our switch. You can imagine this is a router which lives inside the switch. These are our two devices, device in VLAN 10, device in VLAN 20. Okay, VLAN 10, VLAN 20. And what we would do, we would configure a switch virtual interface for each VLAN. So a switch virtual interface for VLAN 10 and a switch virtual interface for VLAN 20. Now when the switch receives traffic, instead of forwarding the traffic to an external device, the traffic is forwarded to this virtual router inside of it. Traffic is forwarded to SVI, to switch virtual interface 10, and then traffic, if this PC was going to communicate with this PC over here, the PCA was going to send traffic to PCB. That same packet, that same data will be sent to SVI 20 to this device over here. So traffic is routed to the SVI interfaces so the devices in different VLANs are able to communicate. And so this is essentially what we're doing. This shows a logical representation of the third method. Now this method, one of the drawbacks is that it is expensive to buy a layer 3 switch. However, nowadays in the market, layer 3 switches are coming down in price, and this is really the main method which is used to allow routing between VLANs, especially if we're going to have a lot of traffic moving between those VLANs. So as we can see here, we would configure a SVI interface for each VLAN. Traffic would be routed to the SVI interface to the virtual router, which lives inside the switch, routed to the other SVI interface, and then routed to the correct device in that VLAN. So now, let's configure routing between VLANs. So we're not going to configure method 1 because method 1 is not used, it's not scalable, it's not a valid method to use. However, it's good to see the methods that are available for us to use and understand why we would choose one over the other. We're going to look at method 2, so we're going to look at configuring router on a stick, and we're going to look at configuring a layer 3 switch for inter-VLAN routing. So I'm going to quickly bring up a console connection to the switch, and we'll get started with the configuration on the switch, and then moving to the router to configure the router for the router on a stick method. So we're on the switch, and so just before I do anything, the connection I've got set up is a router connected to a switch, and I have two machines. Okay, so I've got I've got PCA, which is in VLAN 10, PCB, which is in VLAN 20. I've already put these switches into the correct VLANs, so they won't be able to ping each other because I haven't configured any router on a stick yet. This device is fast Ethernet 0/2, this is fast Ethernet 0/3, and fast Ethernet 0/8 is the link that runs from switch to the router. So on the switch side, what do we have to configure router on a stick? It's pretty simple. All we do is we go into the interface that connects the router to the switch, in this case interface FA0/8, and we use the command switch port mode trunk. That's it. All we have to do is on the switch side for router on a stick, make sure that the link running from the switch to the router is a trunk link, and make sure it supports all the VLANs that I needed. So in this case, that trunk link should support VLANs 10 and 20. Because we're going to be forwarding traffic for those VLANs over that trunk link. So in this case, I'll do switch port trunk encapsulation.1q, switch port trunk allowed VLAN, in this case 1, 10 and 20, and the switch port mode trunk. That's it. That's all we need to configure. That's what we need on the switch on the switch side to configure router on a stick. Now let's move to the router and configure router on a stick from the router's point of view. Okay, so before I move to the router, I'm just going to verify that device A cannot ping device B. So bring up my console connection, my terminal, ping. I've assigned host B the IP address 10.1.20.10. It's in the 10.1.20.024 subnet, and PCA has the IP address 10.1.10.10, and it's in the 10.1.10.0/24 subnet. I ping 10.1.10.20.10. As you can see, the pings aren't working. It's because we haven't completed our router on a stick configuration. So this isn't enough. We need to go to the router and configure the router side for this to work properly. So now I'm going to bring up a console connection to the router very quickly. Okay, so now what? We're on the router. For router on a stick, all the configuration on the router goes underneath the interface, which connects to the switch. So in this case, in our example, we have interface FA0/0, which is the interface on the router which connects to our switch. So if we issue a show run interface FA0/0, at the moment we don't have any configuration under that. We've only got a description which I already put. Okay, so for router on a stick, we don't actually configure any IP addresses under the physical interface. The first thing we're going to do is create our logical sub interface on our router. Okay, so to configure the sub interface, we move from privilege exec mode to global configuration mode with the configure terminal command. And then all we do is type in interface FA0/0, and then to configure a sub interface, we use the dot or the period notation, and we configure the sub interface number, so the logical interface number. Now this doesn't have to be the same number that we're going to use for the VLAN. So in this case, we have VLAN 10 and 20. I'm going to create this sub interface for VLAN 10. I don't have to call it int FA0/0.10. I just have to give it a number to uniquely identify it when compared to the other sub interfaces. However, it makes sense to give it the same number as our VLAN. So in this case, I'm going to give it 10. So in this case, I'll type in interface FA0/0.10. I've created the sub interface now. Now to tell the router which sub interface which VLAN this sub interface is a part of, what VLAN it should expect traffic on. So to assign it to a VLAN, we use the I think it's the encapsulation.1q and VLAN number, in this case 10. So this tells the router that this sub interface is assigned to VLAN 10, and that it should expect to receive traffic from VLAN 10 over this sub interface. Now we just have to assign the subinterface an IP address. So in this case, IP address 10.1.10.1 255.255.255.0, and that's it. So we have configured a subinterface for VLAN 10. Now exit out of this. We're going to do the same thing for VLAN 20. So again, interface FA0/0. And in this case, we want to give it a create subinterface. We use the dot and then give it a number .20. Encapsulation .1Q20, and then IP address 10.1.20.1 255.255.255.0. Exit out of this. Now if you do a show run command, we can see that no configuration under the physical interface, but if you use a .10, there's configuration under the interface FA0/0.10 subinterface, and configuration under the FA0/0.20 subinterface. So all configuration for router on a stick goes under the subinterfaces on the router. The number we use to identify the subinterface doesn't have to be the same number as the VLAN, but it makes sense if we do. And we tell the router what VLAN this subinterface is a part of, what VLAN this subinterface is assigned to, or what VLAN traffic it should expect to receive over this subinterface by using the encapsulation .1Q20 command. So now I'm going to open up a terminal connection again and see if I can ping host B, which resides in VLAN 20. So I've got a terminal connection now. I've opened up my terminal. First, let's see if my PC can ping the subinterface on the router. So ping 10.1.10.1, and it works. So the subinterface works just like a physical interface. The router sees it as a separate interface. Let's see if my PCA can ping the VLAN 20 subinterface on the router. So ping 10.1.20.1, and it works. Let's see if I can now ping PCB, which resides in VLAN 20. 10.1.20.10, and it works. So I can. So as you can see, router on a stick is easy to configure, and it allows devices in different VLANs. It gives them the ability to communicate and share resources and share information. So now I'm able to communicate with PCB. I wasn't able to at the beginning of the video because there was no configuration configured to allow that communication to happen. And by using router on a stick, I'm using a single physical interface to carry traffic for multiple VLANs over that interface. So now let me go back to the so now I'll move back to the switch and we'll examine the state of the trunk interface. So if you look at the trunk interface, show int trunk, we can see FA0/0 is a trunk and it's carrying traffic for all the VLANs. So we're using a single trunk link to connect to our router. So now we have configured router on a stick. Let's configure the most efficient version of routing between VLANs, and that's inter-VLAN routing, or routing via a layer 3 switch. So we're going to use this switch. We're going to change some things around, and I'll be back with you in a moment. So we're back on the switch, and so everything has been reset back to normal. This is what I've got configured so far. Two PCs, we've got PCA and we've got PCB. And PCA is in VLAN 10, PCB is in VLAN 20. They can't ping each other because they're on a switch. So before we can configure multiple switch virtual interfaces, we have to tell this switch that it's a layer 3 switch. In order to do this, we go into global configuration mode, and we have to enable the layer 3 routing feature on the switch. We do this with the IPv4. No, thing is unicast. IPv4 unicast routing. IPv4 routing. Oh, IP unicast. IP routing. So I'm going to pause this quickly and have a checkup of the command. Sorry, so welcome back. Yeah, so the command is actually IP routing. So I was going to mix up between routing a router and a switch. So on a router, you would normally use the IPv4 unicast routing command to enable routing on a router, or IPv6 unicast routing to enable the routing of IPv6 packets. On this switch 3560, it's IP routing to enable routing of IP packets. So once you typed in that, normally you have to reload your switch. So I'm going to pause the video very quickly. I'm going to reload the switch, and we'll be back in a moment. So now the switch has reloaded, and we're back on the switch. Now to configure, so with layer 3 switching, all we have to do, once you've enabled IP routing on the switch, layer 3 routing, all you have to do is go into global configuration mode and configure the VLAN interfaces. Now when you configure the VLAN interfaces, make sure the IP address you configure on the VLAN interface is the same IP address that you give to the device as its default gateway. So now, what we're going to do, we're going to move from privileged exec mode into global configuration mode, and we're going to configure the VLAN interface with interface VLAN, and we give a number. Now this number is important. So before, the number of the sub interface on the router didn't have to match the VLAN number. So in this case, if we were configuring a sub interface for VLAN 10, we didn't have to configure FA 0/0.10. We did because it's common practice and it's good practice. However, we didn't have to. We could have given it the number 100, 200, 300, 400. Didn't matter what number. This time, the number of the VLAN interface matters. Because this configures on the switch directly maps the VLAN interface number to the VLAN itself. So in this case, if we're going to configure a SVI for VLAN 10, we have to give the VLAN interface the number 10. Okay, what we do is configure the IP address command now, 10.1.10.1, 255.255.255.0. Exit, and now let's configure as a SVI interface for VLAN 20. Exact same thing. IP address 10.1.20.1, 255.255.255.0. So we don't have to tell it which VLAN the SVI is associated with. It automatically does that based on the number of the SVI. So in this case, it says that this switch virtual interface has the number of 10. This must be the SVI for VLAN 10. So now it's going to automatically map and associate that with VLAN 10. The same thing with VLAN 20. So now that we configure the SVI interfaces, let's see if PCA can ping PCB. So I've got the command line up to my so the terminal up on my PCA. Let's see if PCA can ping its default gateway. So the SVI for VLAN 10, yes it can. Let's see if it can ping the SVI for VLAN 20, yes it can. And let's see if it can ping PCB, which resides in a different subnet, 10.1.20.10, and it can. So to reiterate, what we have seen is on the local switch we have two PCs connected to it, PCA and PCB. PCA is in VLAN 10, PCB is in VLAN 20. We have created SVIs. The traffic is these are the SVIs for VLAN 10 and VLAN 20. PCA is able to ping the SVI for VLAN 10, ping the SVI for VLAN 20, and ping PCBs which resides in VLAN 20. So we have full routing and full reachability between devices in our different VLANs. So we have reached the end of this video, and we've seen how we can route traffic between our VLANs by using router on a stick and layer 3 switching. We've seen why we would use each one, and how to configure those features and how they work, and we've actually been able to demonstrate that these features have worked and how devices in different VLANs are able to communicate. I hope this has been informative for you, and I would like to thank you for viewing.